We're now going to begin with the second lesson in the chapter on the atom and elements. But first, let me briefly review what we covered in the first lesson. We went back to the ancient Greeks and talked about a couple of philosophers, Leucippus and Democritus, who did thought experiments to come up with the concept of the smallest particle which comprised matter, which they called atomos, or the atom. We then talked about other philosophers, Empedocles and Plato and Aristotle, who had a different view of matter. They described matter in terms of four basic qualities, which they called earth, wind, fire, and water. They focus more on the qualities of matter rather than trying to understand it at its microscopic detail, by assuming that all matter was made of some combination of those four basic earth, wind, fire, and water. Scientists of those days were trying to understand material, and they developed a number of skills in metallurgy and dealing with glasses and ceramics, various applications, including discovering a number of basic medicines and developing things like gunpowder. The field was referred to as alchemy until about the year 1800, when it actually became more of a science, and we will describe that as we go along. We also in the first lesson talked about how we classify matter in terms of being either a pure substance or a mixture. Pure substances could be the elements or compounds, such as H2O, compounds being made by a combination of two or more elements being bonded together. Mixtures could be either homogeneous mixture or heterogeneous mixture. A homogeneous mixture is one that is sort of the same throughout, top or bottom. You can't really separate the components very easily. Whereas a heterogeneous mixture is something where you can easily separate the components, even by filtration or just letting them settle over time. And we gave the example of oil and vinegar salad dressing. Now we want to move on to an important person in the development of the history of chemistry, and this is Dmitry Mendeleev, a Russian scientist. Now, by that time, by the mid-19th century, around 1869 or so, scientists by that time had discovered from nature about half of the elements that we now know to exist. That is, they had discovered about 56 elements. Now, some of these elements had been discovered throughout recorded history. Copper, for example, or in lead and gold, silver and iron. So some of these had been known by man for a long, long time. And carbon was another one that was very old, and tin, and sulfur, which is also called brimstone, mercury, zinc. So some of these had been around for a long time and had been used in metallurgy and to make jewelry and coins and things of that sort. But then around 1800, a number of additional elements were discovered by scientists, and Mendeleev tried to organize all of these elements to try to make some sense of it all. And he organized these elements in a table, which we call the periodic table of elements. And he laid the elements out in terms of their mass, that is how big they were, starting with the smallest and going to the largest. But he also arranged it so that those elements that were similar to each other were stacked on top of each other. Let me show you a quote from Mendeleev. He said, "I saw in a dream a table where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper," which is probably good advice for all of us. "Only in one place did a correction later seem necessary." And the bottom part of the slide shows the periodic table published in a book by Mendeleev in 1871. Now, the modern appearance of the periodic table is shown in the next slide. The elements are all in little boxes, so each one of these boxes represents an element, and you can see that the boxes are labeled with either one or two letter abbreviations. Starting at the top left, we begin with H, which is hydrogen, and then if we go all the way over to the right, we see He for helium. And so the periodic table is laid out in what we call rows. So hydrogen and helium, being first to come to class, got in the first row. And in the second row, we have, if we go back to the left, we have lithium, Li, beryllium, Be, and then going over to the yellow, B for boron, and then carbon, nitrogen, oxygen, fluorine, neon, that is the CNOF and Ne over to the right, as the second row, and then we can go to the third row and the fourth row, etc. The elements are arranged in the periodic table in terms of rows. Now these begin with the smallest elements, hydrogen being the smallest, and then helium the next smallest, and then lithium the third, beryllium. They are arranged in that order, but also, and this is what is key to the periodic table, the elements which are similar to each other are stacked on top of each other. So if we go over to the left and we see Li for lithium, right below lithium we see Na. Na stands for sodium, and you've probably heard of sodium as a component of sodium chloride. And then below that is potassium, K, and you may have heard of potassium. And the lithium, sodium, potassium all have very similar properties. And likewise, if we go to any one of the columns which we call groups, the properties of the elements are similar from top to the bottom. Now they change a little, but they are similar. Most interestingly, if you look at the far right, where we have helium, He, and then neon, Ne, Ar is argon, and Kr krypton, which of course you probably remember that's the planet on which Superman was born, was called Krypton. That the elements on the far right are called the noble gases. Well, first, they're all gases, but secondly, they are very inert, are unreactive. So we call these the noble gases or the inert gases. They do not tend to react with anybody else in the periodic table. Okay, now, so we have rows and we have columns or groups. At the top we have the smallest elements, and at the bottom we have the larger elements. You will notice the two rows that are at the bottom, that are sort of like the balcony area. These are some larger elements that we won't really deal with very much, so don't worry too much about them. And also, I want you to not panic, because there's 114 or so elements. You're not going to be expected to know the abbreviation of all of these, although there will be a number that you probably know, and you probably should have some familiarity with ones that are quite common that we deal with in our everyday lives. Iron is Fe, copper is Cu, gold, you need to know gold, is Au, silver is Ag, sodium, potassium, calcium, magnesium. These are elements, or a form of these elements, we talk about a lot with respect to our health or in nutrition. So sodium, potassium, calcium. And you may have heard of other metals such as nickel and zinc and chromium, and of course probably tin and lead and mercury. Also, you've no doubt heard of carbon, which is C, oxygen, very important, which is O for oxygen, nitrogen, which is an N, and then maybe a few other of the ones on the right, such as neon and helium. Helium, of course, is what we use to fill the balloons for parties, so you need to know that one. Okay, but all of the others are just the other players of the game. Now, the periodic table shown is color-coded. They're not all color-coded, but I picked one that was color-coded. All the ones in light blue are what we call metals. Now, a metal is something that is generally a solid. There's only one that is a liquid, and that happens to be mercury. But all of the metals are solid. They generally look metallic looking, or grayish or silverish. There are a couple that have a yellow tint to them, copper and gold. But most of them are grayish looking. They look like iron. And it would be difficult to distinguish a lot of the different metals just from their appearance. They also conduct electricity, as we've talked about before. So the metals are in blue or light blue, and the nonmetals are in the upper right-hand corner, and they're in reddish color. And they're distinctly different elements from the metals. That is, can exist in a variety of phases. They can be either solids, like carbon is a black solid, or carbon also exists as diamond. Or they can exist as gases, such as nitrogen gas and oxygen gas and neon and helium gas. Or a liquid. Bromine is a liquid. But they definitely are not metallic looking. They are non-metals. And then, of course, you have to have elements that are sort of in between the metals and the non-metals, and those are the ones that are shaded in yellow, and they're called metalloids. That is, sometimes they behave a little bit like metals, and sometimes they behave like non-metals, and so we just place them in the boundary between those two large groupings. Now, I said there are about 114 elements. Actually, in some textbooks you will see a larger number. That's because scientists are constantly trying to create new elements. I've seen as high as 118. But again, not to worry, because the ones that are at the very bottom, and you may notice that there are some of these don't even show a name, and that's because they haven't decided on the name, or they haven't decided if the species exists long enough to be given a name. These are not ones that we deal with in our daily lives. The next slide is a representation to show you what some of the metals actually look like. And if you look over to the left, you see a lot of them look like this grayish, silverish kind of metal. You can see a couple that are the more gold looking or copper looking, more yellow. That actually is copper and gold. Some of them have pictures of people's heads, and that's because it's actually representing the person who discovered the element. They don't really look like those people. Up at the upper right hand, you have the nonmetals, and several of these are gases, especially the ones on the rightmost group, the noble gases or the inert gases, and they are shown represented in tubes like they would be a neon sign, because in fact that's how we use neon as in fluorescent lights. Others are gases as well, such as nitrogen and oxygen. So that just shows you what they look like. Now, we chemists have to have fun occasionally, so if we have the periodic table of elements, we have to also have the periodic table of the elephants. And if you look carefully at some of these cartoonish drawings, you'll see, for example, that in carbon, the elephant is grilling using charcoal, which is carbon. For oxygen, the elephant is scuba diving with a tank of oxygen, no doubt. And iron, he's hammering with a hammer and a nail. So this is just a little fun way to represent the various elements. Okay, now we're going to take another break, and we have some questions for you to answer before going on to the third lesson in this chapter on the atoms and elements. Thank you.